Hi everybody, in this video I'm going to show you how to use linearization techniques to solve physics problems. So recall some of the key ideas that we need to keep in mind when we're using linearization analysis. That is, fitting a straight line to data and using the slope of that line to figure out something important. And sometimes the data themselves might not even be linear. So what you need to do is create a mathematical model of the physical quantities that are being represented by a table of data. And the idea is that that's what we mean by mathematical model, is we're talking about an equation that relate variables in the table with respect to each other. And then determine how to rearrange your equation so that in the end you're essentially going to have it in the form y equals mx or y equals mx plus b, where y might be some complicated term, x might be some other complicated term, and the slope is what you're really trying to calculate, and that b is going to be some constant term. So there are going to be situations where sometimes this will be easy. For example, if you are trying to make a plot of the force acting on a massive object and versus the resulting acceleration, well, you're going to get from F equals ma, that's just going to be a straight line. But a lot of times that's not quite so easy. In that case, the straight line would have a slope equal to the mass of the object. But what if you were to make a plot of the kinetic energy of an object as a function of its speed and use that to try to calculate the object's mass? Well, plotting k versus v would not be a good idea because that would end up giving you a parabola. But if you were to plot k versus v squared, in other words, you made a new column of data in your table and just squared every v value to get a v squared, and you plotted k versus v squared, the slope of that plot would end up being half of the mass. So therefore mass would be equal to 2 times the slope. So that's what we're talking about by turning these functions of variables into things that are linearly related. And then the slope of that graph is going to be used to determine whatever you're going to determine. Let's look at a big example to illustrate all of these ideas in practice. So here, consider a Van de Graaff generator. So you measure the idea is to measure the amount of charge on the 6 centimeter diameter sphere of a Van de Graaff generator. And to do so, you're going to use a spring with a spring constant of 0.65 newtons per meter, launching a 1.5 gram bead horizontally toward the sphere, and you can charge that bead to a certain predetermined charge, 2.5 nanocoulombs. And the idea is to measure the bead's closest approach using a high-speed camera as a function of spring compression distance. And upon doing that, you get the following data table that's shown right here. So what are we to make of these data? I mean, you notice that as this goes up by 0.3, this goes down by about a factor of 2, actually more than that. And then as this goes up by another 0.3 centimeters, this goes down by a factor of, well, less than 50%. And then this goes up by another 0.3 centimeters, and this suddenly goes down by 75%. So what's going on here? Well, here's where we make our mathematical model. So we're using energy conservation here. In other words, the compression amount of the spring determines how much kinetic energy the bead is going to have. And its closest approach determines the amount of potential energy it has there as well. Well, energy conservation says that these are the same. I mean, you start off with elastic potential energy that turns into kinetic energy after you spring the spring, and then that's going to turn back into electric potential energy upon closest approach. So here's how I work this out. I say, okay, the total energy at any one point is equal to the total energy at any other point. So how about I pick my 2 points, one being when the bead is safely compressed in the spring before it's released, and the other point being the point at closest approach. Why am I picking those 2 points? Because I'm presuming that first of all, I'm presuming that my spring is far enough away from my Van de Graaff generator that there is no electric potential energy at the time that the bead is released. And it's also not moving at the time that it's at maximum compression in the spring. So all of the energy is elastic potential energy, that is spring potential energy. At closest approach, well, closest approach means that it's at the turning point. It's no longer moving there. And that means that there's no kinetic energy. Also, it's no longer in the spring, so that term's going to be 0 as well. All of the energy at that point is electric potential energy. So I've zeroed out my 0 terms, I've plugged in my expressions for these potential energies, and what I'm left with is 1/2 k s squared equals k q1 q2 over r. Well, what about these k's? These are very different k's. For my electric potential energy, I'm using the Coulomb constant k, 1 over 4 pi epsilon naught. Whereas for the elastic potential energy, the spring potential energy, I'm using my spring constant k. So I've denoted these by appropriate subscripts so that there isn't as much confusion as there might otherwise be. And I'm calling my spring compression distance S. That's actually what is in the table here. S is directly in the table. Now, what about closest approach? Is that R? That is not R. Remember that the diameter of our Van de Graaff ball was 6 centimeters, which means that the radius of it is 3 centimeters. So this little r, that distance of closest approach, that's the distance to the center of the sphere, which is equal to the radius of the ball plus the actual distance of closest approach, d. Little d is what's in this table right here. That's what I need to be worrying about. So now that we have things in terms of what's in the table, how does this look? Well, little r is big R plus what I'm calling little d, the right-hand column of the table. Nothing changes on the left side. So how can we get a straight line? Well, little d is in a denominator and it's added to another thing that's constant. So what I need to do is I need to say, okay, I'm going to call my vertical coordinate s squared, s initial squared, and I'm going to call my horizontal coordinate 1 over r plus d. In other words, just rearranging this equation, if I graph s initial squared versus 1 over r plus d, where big R is the radius of our Van de Graaff ball, then I will get a straight line whose slope will be equal to 2k Coulomb q1 q2 over k spring. So that's the plan here. How do I enact this plan? I need additional columns. So remember that at the end of the day, we want to get Q2 by itself. We're asked for what the charge is on the Van de Graaff generator. That's the unknown charge. So solving for Q2 upon recognizing that everything that's multiplying our 1 over r plus d is the slope. We have slope is this stuff, so therefore Q2 is spring k times slope divided by 2q1 times Coulomb k. So I need to make new columns. My new columns, what I really need is a column for 1 over r plus d. Well, d is given. R is just the radius of the Van de Graaff sphere, so just add 0.03 meters to each of my little d's right here, so there's my big R plus d. But I don't want big R plus d, I want to graph versus 1 over big R plus d. If I just graphed s squared versus big R plus d, I would get an inverse plot. If you try fitting a straight line to an inverse plot, go directly to jail. So now I also need to remember this is s right here. I need a column for s squared. So I made a column for s squared right here as well. Notice that I've converted everything into SI units as well. That is meters, inverse meters, etc. So there's my column, or my set of columns. So remember I'm graphing s squared versus 1 over r plus d. After doing that, this is what I got when I plotted these points in Excel. The straight line, though, I actually drew that straight line myself, which is what you would need to be able to do on, say, something like an AP exam or a final exam or something like that. I drew the straight line myself. I just copied the Excel plot into Microsoft Paint, and I took their straight line, which is automatically straight, so that's essentially my straight edge, and I fit these points as best as I could. Well, what do we do now? We need to calculate the slope of this straight line. Now, how do you calculate the slope of the straight line? Oh, take 2 points on the line. Well, don't take data points. The data points are not exactly on the line. Yeah, there are a couple of data points that are kind of close to the line, but they're not exactly on the line. So what do? I take other points that I can readily identify, points that are as far away from each other as possible. Well, there's one. Looks like my straight line goes through the origin. That's nice. And there's another one over here at the top. Now, the way that I ended up determining this point, of course, the origin is 0, 0. The other point, when I put on some fine mesh lines into that plot, I determined that the horizontal value there was 32.6 inverse meters, and the vertical value was just given on the plot right here. But notice, yeah, the units 1 over distance is going to have units of inverse meters, or, well, inverse meters in SI units. And I got that this was 32.6 when I put in additional lines in here in my Excel program. But anyway, the vertical part of 0.0007 meters squared, that's easy to see. That was the whole point of doing this, no pun intended. So slope is change in vertical divided by change in horizontal. Well, the vertical is 0.0007 minus 0. The horizontal, well, remember that final value was 32.6 inverse meters. The initial value was 0 inverse meters. So taking those numbers, there is my slope. Yay, I have my slope. 2.147 times 10 to the minus 5th cubic meters. So again, kind of funny units there, but whatever. I mean, volume, but small amount of volume. So my slope has units of volume. I mentioned this is funny units because technically that's not so much of a volume. It's more like an area per inverse change in position. That's really how you should be thinking of this. So yeah, I know that that has dimensions of volume, but it's not really a volume. That's why I say that that's funny units. So anyway, the spring constant, the problem, that's given. Remember, I just took this equation from the previous slide after solving for Q2. Coulomb constant, well, that's about as given as things are, 8.99 times 10 to the 9 meters squared per coulomb squared. And the charge on the beaded sphere is also given. That's the one that we can reliably charge. That was the 2.5 nanocoulombs. So now that we plug all this stuff in, we get the value of our Q2. And evaluating this, by the way, making a quick check that the units work, we have newtons canceling, we have meters in the denominator here, meters squared in the denominator canceling out these meters cubed, and we get 1 over coulombs per coulomb squared. That just cancels out to give coulombs. So the charge ends up having units of coulombs, as it should, and when you plug in the numbers, you get 3.1 times 10 to the minus 7 coulombs. That is about 311 nanocoulombs, or 0.31 microcoulombs. So that is how you can solve for an unknown quantity using linearization techniques. And this also would have worked, I mentioned at the beginning that you're not allowed to be able to add on extra terms, just going back to our original equation here. If we had, say, like a plus 5 nanocoulombs or something like that, that wouldn't have affected our slope. It's just that all of our points would have been displaced upward by 5. Well, what I meant in this point early on here about you're not allowed to add anything to, like, any extra terms. What I mean is extra terms that have the variable that you're looking for in them. For example, in this case, what if I had a plus 2r plus d squared, or plus 2 times constant times r plus d quantity squared? Well, then I would have the variable that I really care about in 2 completely separate areas to 2 completely separate powers, and each of those separate terms has different terms multiplying it. That wouldn't be kosher. I would not be able to use linearization to solve that problem. And at first, somebody might think, well, how was I able to use linearization to solve for this? Well, that's because I had one constant term, a term that I knew about, added to my variable. So I simply made this whole thing a variable, kind of like a U substitution, and then just graphed versus that. Well, versus the inverse of that. So that's what we mean by extra terms. So anyway, that is how we use linearization to solve for unknown quantities based on these slopes of graphs. So hopefully that was clear enough. If not, please leave your questions in the comments section of this video. And thank you for watching.